It's a great pleasure to be here. Thank you for inviting me, and John's given a very nice start to this. So I've got two talks, and they will touch some but not all of the issues that John commented on. So infinities occur in many physical theories, and they used to be treated as a disaster, but nowadays some people seem to treat them as a virtue. And problematic issues, however, arise as regarding such infinities. So I've got 7 topics: infinities in general, infinities of size, the infinite universe, existence of an infinite multiverse, infinities of size, small universes, infinities in isolated local systems, infinities of age, and infinities at the small. And today and tomorrow will split in the middle. So infinities in general. Infinity refers to something without any limit. It's a concept relevant in a number of fields, predominantly mathematics and physics. I think I lifted this from Wikipedia, by the way. The English word infinity derives from the Latin infinitas, which can be translated as unboundedness, itself derives from the Greek word aperos, meaning endless. In mathematics, infinity is often treated as if it were a number, i.e. it counts or measures things in infinite number of terms, but it's not the same sort of number as the real numbers. And that's absolutely crucial. I think a lot of us have been misled. Because we have a symbol, we think we can treat it as just another number. And the big theme of my talk is that infinity is not just another number. It's something, a completely different kind of animal. The true nature of infinity, it is not a very large number. It's an entity that can never, ever, ever be obtained. That's the crucial thing. It is always beyond the bounds of the possible. And I think that's what sometimes has been forgotten in our modeling. What's the largest number that's meaningful in physics? Well, the number of protons in the physical universe, 10 to the 82, that's an astronomical type of number. The number of string vacua, allegedly about 10 to the 500. And you can form a much, much bigger number. So supposing you take that number of string vacuums, take it to the power of itself, throw in a factorial just for good measure, you've got an incredibly large number. You still haven't taken the first step on the road to infinity. Once you've measured all of that amount, you've gone that distance, as far as infinity is concerned, you haven't even begun. And that's what we seem to forget when we talk about infinity. Biological numbers are much larger than physical numbers. There are immense numbers, as Ellis has emphasized. For example, myoglobin, 20 different amino acids, a chain, the length 150 amino acid residues. They're 20 to the 153, that's about 10 to the 200 possible theoretical chains. Myoglobin is one of these. But myoglobin is a small molecule. There are much, much bigger molecules such as DNA, much bigger space of possibilities. The numbers you get are much bigger than astronomical numbers, which is why Ellis called them immense numbers. They are still not infinite. Now, the idea of a googol is a large number, a 1 followed by 100 zeros. A googolplex, the second largest number with a name, a 1 followed by a googol of zeros, and a googolplexion, the world's largest number with a name, it said a 1 followed by a googolplex of zeros. These are much, much bigger than anything in physics and anything in biology, but I keep saying this and you're going to get bored with me saying this. Go that distance, you haven't even begun on the way to infinity because there's still an infinite number of those steps. That step has not got you anywhere on your road to infinity. And according to Wikipedia, something I didn't know, the world champion largest number listed in the Book of Records is an upper bound derived by R.L. Graham from a problem in a part of combinatorics called Ramsey theory. Graham's number cannot be expressed using the conventional notation of powers, and powers are powers. If all the material in the universe were turned into pen and ink, it would not be enough to write the number down. And I won't go through all of this. You use a notation that Donald Knuth developed where 3 to the power 3 means 3 cubed. You get 3 to the power 3 and so on. It's all, you get towers of exponents, and you build up these towers of exponents, and you continue the process of towers of exponents. 63 steps down is Graham's number, which is apparently perhaps the largest number. I'm not sure about this, but maybe the largest number which has been used in a mathematical proof. And you can't write it down, but you can give a derivation how to get it. It's much bigger than any number that occurs in physics or biology, and it still, as I keep emphasizing, hasn't even begun to start you on the way to infinity, because once you've gone all that way, there's still an unbounded number of left beyond you. So I'm going to keep emphasizing this, even if it bores you, because this is the nub of the argument. Infinity is not a big number. The true nature of infinity is an entity without limit, hence its paradoxical nature. So write down infinity, a series of ones which carries on without limit. Shift all the ones forward one place and you get a 0 there. Add a 1 into that 0 and you've got the same series you started with, because they just kept on going for infinity. So infinity plus 1 is equal to infinity. That's the paradoxical nature of infinity. Therefore, infinity multiplied by any number is infinity. And of course, that's not the same as any number. It has, and John was emphasized, this a duality to 0, and the paradox is relating infinity and 0 all the time. And just as infinity is questionable in any physical context, well, in most physical contexts, 0 is often also a questionable context. For instance, the idea of 0 size is dual to the idea of infinite size, and they're both equally problematic. And they have similar problematic properties. If ax is equal to x, when a is not 1, you have two options. X is 0 or x is infinity. So they both have this kind of paradoxical thing that they don't do what ordinary numbers do. Now this leads to these paradoxes, and I'll just quote one which John has written about beautifully in his books about this, Hilbert's paradox of the Grand Hotel. If a hotel with infinitely many rooms is full, it can still take in more guests. And this is typical of the kind of paradox that arises with infinity. And so what I want to emphasize here is in infinities, in the use in physics, there are essential and inessential uses. And I think it's really important to distinguish between the essential and the inessential uses of infinity. And there are three types of issue. The use of infinity in physical argument in an essential way. Does a proof depend on the paradoxical nature of infinity? In other words, does a proof of anything depend not on the fact that it's a large number, but use those paradoxical properties? If so, that's what I would call the paradoxical use of infinity, the essential use of infinity. Alternatively, in many arguments, infinity does not use those paradoxical properties. It's just a holder for a very large number. Okay, so there are these two different uses of infinity. Some uses where you really use those paradoxical properties, and some where you don't. You're just saying basically this is a very large number. And that's in physical arguments. The physical existence, can infinity actually exist? This is what we're going to be talking about. Can anything in the universe be infinite? Can an infinity come into existence? And that relates to the, can a singularity exist? The points in a line which John mentioned, can there actually be an unbounded infinity of spatial points, of physically real spatial points between my fingers? Can fractals exist? Because fractals, to be a proper fractal, it has to continue without limit upwards and downwards. So the fractal idea has got an infinity built in. And can the universe exist infinitely? So this is the physical existence of infinities. Whichever you say, one point which I will emphasize, supposing you claim there is an infinite of anything, an infinitely small, infinitely large, infinitely many, you will never be able to prove it. You can't prove infinities exist because no operational procedure to establish the existence of infinities can be carried out in a finite time. Why? Because you've got to count them. You've got to show that there's an infinite. No matter how many you've counted, you haven't finished the job because you've got to keep counting forever in order to prove there's infinity. So if infinities do exist, you can't prove their existence by any experiment. So therefore, is it a scientifically meaningful concept? I'm afraid I'm a hardliner about experiments. I take the view that science is to do with things that are provable, that are measurable, that are somehow you can give evidence that they exist. And in my view, if you claim infinities exist in a physical sense, and I'm going to give you a lot of different arguments about this, but I claim it's a philosophical, not a physical claim, because there isn't any experiment that you can use to prove it. And there isn't any experiment because there just isn't any conceivable way that you can show that you would keep going forever and never, ever, ever reach a limit. You can't prove that by any experiment of any kind, whether it's a large infinity or a very small one. So the claimed existence of physically existing infinities, I emphasize repeatedly, it's an unattainable state rather than number. So we heard already that Aristotle talked about it. David Hilbert, the infinite is nowhere to be found in reality, no matter what experience, observations, and knowledge are appealed to. And Hilbert, of course, was totally aware of the use of infinities in mathematics, but does it exist in physical reality? And Hilbert was absolutely sure about this. It is nowhere to be found in reality, no matter what experiences, observations, and knowledge are appealed to. And that is also my own position. The claimed physical existence is, as I've said, not a scientific statement if science involves testability by either observation or experiment. Yes, it's useful in mathematical context, but then it leads to all sorts of paradoxes. But what's the relation of that mathematical infinities to physical infinities? So I've emphasized the essential and inessential use. Sometimes you mean by infinity it's a number which is bigger than any physically relevant quantity, or something that is smaller than any physically relevant quantity. And so, for instance, asymptotic flatness, you take r goes to infinity to look at outgoing radiation conditions or asymptotic flatness. That's an inessential use of infinity. You're just using it actually to stand for a large number. It doesn't use those paradoxical properties. So that's what I call an inessential use of infinity. The genuinely infinite depends on its paradoxical properties. And my position is that the former, when it's an inessential, you shouldn't use infinity. You should replace infinity by a very large number and use that number, talk about that number. Because thinking what that number is teaches you things about the physics of the situation you're looking at. And so if it's the inessential, don't talk about infinity, talk about the number, which is the number where you have reached effective infinity. If it is genuine infinity, it's depending on those paradoxical properties. My position is that this is an argument which isn't a valid argument in physics. It is one which should be dropped and abandoned. So the basic guidelines, what I call Hilbert's golden rule: infinities do not exist in real physical systems, and the infinity fork. If the use of infinity in physics is essential, it uses those paradoxical properties, then, in my opinion, that argument should be discarded. If the use of infinity is not essential, replace it by a large number in effective infinity and see what happens. Work out what in infinity is, and that is good physics, because you then have to relate it to real physical issues. And so I'll try to illustrate this viewpoint in my further discussion. Now, as a warming up exercise, I'm going to talk about something outside my domain of competence, but nevertheless interesting, which is infinity in language. And I'm going to refer particularly to an article by Kamarova and Nowak, talking about that fact that they claim there are an infinite number of languages contain an infinite number of sentences, and they use that to deduce properties of learning. They use this in this article, Language, Learning and Evolution, to talk about learning and evolution based on the idea that there are an infinite number of languages, each containing an infinite number of sentences. Now, this is an essential use of infinity. And they say natural languages are infinite. It is not possible to imagine a finite list that contains all English sentences. And this is based on the idea that sentences can have an unbounded length. You can just keep adding subsidiary clauses ad infinitum to obtain arbitrary long sentences. And this, of course, is what formal language theory does. But such a sentence is not really a complete thought until it's complete, but it never will be complete, because that's what infinity means. So if you have an infinite sentence, you never reach the end, and so it never is a completed thought. This has nothing to do with real-world biologically usable languages, for the simple reason the human brain has finite storage capacity and only survives for a finite length of time, can only carry out a finite number of operations in its lifetime. Hence, there's a finite limit to the length of a possible sentence in a biologically realistic language context. While sentence is actually usable for communication purposes, which is the raison d'etre of languages, the reason we have language is to convey information, they are very, very much shorter. And the same kind of restriction applies to any real digital computer. The hypothetical infinite tape of a Turing machine is equally unrealistic. The computer won't last for an infinite time. It won't be able to read an infinite tape. The infinity of that tape is a meaningless concept because it cannot be realized in any realistic situation. And that's incidentally in a sense, it's part of the halting problem. Now, there's a strong claim made in that paper I've mentioned, that Gold's theorem, which is a theorem that there exists no algorithm that can learn the set of regular languages, proves the necessity of the existence of an innate universal grammar in the brain that has been provided us by evolutionary processes. It's a very strange claim that they're making. You have your formal theory of languages. You have a theorem called Gold's theorem, which says there's no algorithm that can learn the set of regular languages. From that, you claim to deduce properties in the brain of the existence of modules, which is a universal grammar, the Chomsky kind of thing, which has been given to us by evolution. So it's a very strange line of argument. Now, the Gold property, a class C of languages has the Gold property if and only if C contains a countable infinity of languages. Note the infinity there, such that Li is less than Li plus 1 for all I, and a further language, such that L infinity, such that X is a sentence of Li only if it's a sentence of L infinity, and it's a sense of L infinity only if it is a sequence sentence of Lj for some j. The details don't matter. The point is, this argument, Gold's argument, depends crucially on the idea of languages being infinite with infinite length sentences. Now, you can calculate an absolute limit on what a human being can possibly read in their lifetime by estimating how many words can be read by a machine doing so continuously for 24 hours a day for, say, 120 years at a rate of, say, 10 words a second. And you get 200,000 words. You get a very large number. It's not infinite. It's not even the first step on the way to infinite. The set of possible languages is not infinite because the set of possible thoughts is finite, because the brain is a finite system and it only lives for a finite time. And if you're realistic about any of this, any claim that the set of possible thoughts is infinite is unrealistic. The claim that there's an infinite set of languages is completely unrealistic. In fact, given the famous features of short-term memory, there's a wonderful paper by Miller called The Magic Number 7 plus or minus 2, Some Limits on Our Capacity for Processing Information. One can estimate that a maximum length understandable sentence has 7 subclauses, each with a maximum of 7 words. So 49 words is the length of a sentence that you can actually understand. As sentences become longer than this, they become increasingly ununderstandable as a function of the sentence length, and hence unusable for communication purposes. So one is probably safe in saying that a sentence more than an order of magnitude larger than this, 10 times 49 is 490 words, is of no use for communication purposes, and will not occur in any real language except as a possible flowery demonstration of verbal dexterity intended to impress the reader rather than being intended for genuine communication. Phew! That was 115 words. It should have been split between the words, between the words as in purposes and so on. And the point is, Peter Gordon, Learnability and Feedback, in the journal called Developmental Psychology. If a language learner is presented only with text presentation, i.e. grammatical strings only, then of the handful of language classes considered by Gold, it can only identify languages from the finite cardinality class. This class of languages does not include any language that had an infinite number of sentences, like, for example, English. This is absolute rubbish. It is not possible for there to be an infinite number of meaningful sentences in the English language. These people have forgotten what language is about. Language is about communicating information from you to me, and by the time you reach the end of the sentence, you must remember what was at the beginning of the sentence. These statements and theorem have nothing to do with real-world language learning. The claimed modularity result, which is a biological result which is claimed to follow from these mathematical theorems, is wrong for a host of reasons to do with the way biology works, and this claimed mathematical proof does not do the job because it's based on the essential use of the idea of infinity. Of course, you can't learn an infinity of languages in a finite time by any possible step, but that's not a real-world task. It's got nothing to do with children and learning of language. For reality, see biologically realistic discussions such as Jerome Feldman's book, From Molecule to Metaphor, A Neural Theory of Language. So that was a warning example about using the idea of infinities in a context where they don't actually make sense. My second warming up example is mathematics, and this is a positive one. In my view, the transition from calculus to analysis was one of the most important developments in the theory of mathematics and its applications in mathematical physics. It underlay the development of powerful new tools and results in mathematics. Now, the key step was going from calculus, where you had limit n goes to infinity and limit delta t goes to naught. You abandon that. You replace those infinities and that zero by epsilons and deltas. For epsilon greater than naught, there's a delta. epsilon greater than naught and an n epsilon such that. And you calculated how big delta would be, and you calculated how big n had to be, and that's how you engaged with the real nature of the mathematics that was going on. It leads to function spaces, existence theorems, and all the rest of it. So the good mathematics lies in the working out of what the delta is and the n is, and that's replaced that limit as n going to infinity. And that's where much more powerful mathematical results came from, abandoning the infinity and using, in fact, so these were inessential uses of infinity. If it's an inessential use of infinity, replace it by a big number in n or a little number delta and work out what the consequences are, and you learn much more than if you have that idea of the limit n going to infinity or the limit delta t goes to naught. And so what I'm proposing, the same transition I'm talking about here should be done in physics. Replace limits by estimates of what values give what accuracy. So that's my starting point. Now, infinities of size, what about the infinite universe? The k is naught or k is minus 1 Robertson-Walker universes are naturally infinite. They have an infinite amount of matter, an infinite number of galaxies, but we can't see with them or interact with them because of the existence of particle horizons and visual horizons. The early universe is opaque, we can't see back earlier in that time, we can only see out to a certain distance. And we have this picture using a conformal diagram. We're there and now, that's our world line. There's a distant galaxy there. So there's our world line, that's the decoupling, that's the start of the universe. And that's the last scattering surface. This is the hidden part, that's the start of the universe, that's nucleosynthesis in the very early universe. The most distant part of the universe we can see is the two-sphere that the COBE satellite sees, and we can't see anything out further than that matter there, so anything out here is invisible. And so we can see out to a finite distance. So supposing the universe is infinite, you can't prove it because you can only see out to a finite distance. Furthermore, the stuff out there has no causal effect on this, which is a theme I will pick up in the next talk. If you stick to those infinities, you get these paradoxes, and I wrote about this a very long time ago with my colleague Jeff Brundrett. The genetic code is finite. So if you have an infinite universe with a finite probability of life existing, after a certain volume, you will have used up all the possible genetic codes because the genetic code is finite. So in the next volume, you have to repeat genetic codes you've already used. If the conditions stay out there, we all have genetically identical twins necessarily in a volume large enough because the genetic code, all possible genetic codes will have been used in a big enough volume. The next volume will be repeating genetic codes which have already been used. Once you've got a volume like that, it's 100% certain we each have an identical twin out there in the genetic sense. But of course, the paradoxical property of infinity is that there will then be an infinite number of these identical boxes. So then we each have an infinite number of genetically identical twins. There are an infinite number of such volumes V. And of course, then you can ask, well, what kinds of histories will they have had? Well, there will have been different histories, but in a finite volume, there's only a finite number of things can happen. And the histories will repeat as well. And so this is the kind of claim which we've heard in the case of chaotic inflation, that what is going on in this room is going out infinite number of times out there, so almost identical, differently, and so on. That's an inevitable consequence, if you like, of an infinite universe where things continue exactly the same all the way out. If the cosmological principle holds in a strong sense, there's an infinite number of me and an infinite number of you, or at least identity, all out there, doing the same things, doing different things. This is a disconcerting kind of statement, but it's quite untestable. It has no relation to any testable observation of any kind, not related to any physics observation or experiment. Now, when we wrote this paper, we used this as an argument, as a philosophical argument against infinite universes. Now, you avoid this if you have closed space sections which have no infinity. You keep going round and you arrive back. And Einstein, of course, specifically used the KS+1 model in order to get compact sections. That was the prime reason he made his model the way it was. He was trying to deal with boundary problems, with boundary conditions of infinity, and he solved the problem of boundary conditions of infinity by having closed space sections because he had a Robertson-Walker model with KS+1. And John Wheeler picked this up and took this as a basic assumption in cosmology. It must be that cosmology is finite because it solves so many paradoxical problems. It gets rid of so many divergences. And John Wheeler wrote this book called Einstein's Vision, in which he developed this at great length, and saying that it's crucial to cosmology that the only models that make sense are ones that are spatially closed. In fact, many of you will have read Misner, Thorne and Wheeler. Now, you may or may not have realized the cosmology section of Misner, Thorne and Wheeler only treats K is +1 models. The K is -1 and K is 0 models are relegated to a chapter on other models. And in fact, Misner, Thorne and Wheeler, the assumption is that K is +1 was the only ones that make sense. If you have those closed models, it puts global constraints such as the total charge must vanish because you integrate Gauss's theorem. It banishes divergences. There's a finite number of galaxy stars at people, and you avoid all of these problems. And so philosophically, and of course that doesn't prove anything physically, but philosophically one can have a preference for closed models where this doesn't occur. And Einstein had this view, Wheeler had this view, and personally I also have this kind of view. The finite universe removes the divergences. The divergences go because there's a finite age leading to a visual horizon, a finite size, so that forces converge if we use the potential formulation. But it's really interesting and important to remember, you don't have to have K is +1 universes to get finite. You can have K is -1 and 0 models that are also finite. And the point is, Einstein equations are local differential equations. They determine the local geometry, but they do not determine the global topology. And so Robertson-Walker space-time has R cross sigma, where sigma is the spatial section. That can have the universal covering space, a flat space, a sphere, or a hyperbolic space. But it can be compact in any of these cases, and that's been known for a long time. You can have compact spaces with K is 0 and -1, as well as in the case K is +1. And in that case, there are no physical infinities. There's a very nice review of this by Lachaise, Ray, and Luminet in Physics Reports. One of the big questions, one of the unknown questions, which would be a tremendous step forward, is if we could come up with a mechanism which determined the topology of the space sections in cosmology. We have no mechanism, we have no rules for determining that, and these topologies can get incredibly complicated. Karl Schwarzschild in 1900, one could imagine that as a result of a normalcy extended astronomical experience, the entire universe consists of countless identical copies of our Milky Way, that the infinite space can be partitioned into cubes, each containing an exactly identical copy of a Milky Way. Would we really cling on to the assumption of infinitely many identical repetitions of the same world? We would be much happier with the view that these repetitions are illusory, that in reality space has peculiar connection properties, so that if we leave any one cube through a side, we immediately re-enter it through the opposite side. Pac-Man rules supreme. And this is the kind of picture that you can have a basic cell on the left where you identify the opposite size. You can go to the universal covering space, which is on the right, and then you have a group of identifications there. And so the small space in which you go out the one side and come back is equivalent to the infinite space with a group of identifications. So the repetition of a basic cell with opposite edge identified creates an effectively infinite universe, but it's compact. There's a finite amount of matter in it and no infinities. And so it's really crucial for this argument that we can have Robertson-Walker cosmologies with any value of K which are compact. It does not follow, because K is 0 or -1, that there's an infinite amount of matter in the universe. Let's go to some of the divergence, and one of the oldest divergences was Olber's paradox. The basic point of Olber's paradox, why is the sky dark at night, is the need for integration over all very distant sources and determining the intensity of integrated radiation from astronomical sources. Those distant sources cannot be neglected in flat space-time, which Olber's assumed, because their number goes up as r squared, and this compensates for the decrease in flux from each source, which goes down like 1 upon r squared, where r is the standard radial distance in flat space, and this diverges. Each shell of thickness dr contributes the same amount of light no matter how far away. If you allow for the intervening matter, stopping all of that light coming in, and you do the sum, then the idea is the entire sky should be as bright as the surface of the sun. And so this is Olber's paradox, the number of sources, the volume in that volume is 4 pi r squared dr, the flux goes down as 1 over r squared, each shell gives the same energy flux and it diverges. Doing the calculation in a Robertson-Walker universe with r chosen, the area distance gives the same result. Because the reciprocity theorem, which holds in any space-time, shows that this relation will be true in any curved space-time. This pointwise specific intensity of radiation received in a direction theta phi is given by the intensity Ig where it was emitted, the spectrum redshifted divided by 1 plus z cubed, where I is the source spectrum, Ig is the surface brightness. And here we see the resolution of Olber's paradox, well, partial resolution in the expanding universe. The very distant sources at high z appear much fainter because you've got your factor 1 plus z cubed, which knocks them off. But it's also the fact that you hit a boundary, you go down a certain distance and you come to the end of the sources. There aren't any more sources to look at. So the sources we can see in our past light cone are finite, and they lose light according to 1 plus z cubed. Hence, in an expanding universe, very different sources at high z they appear much fainter than nearby ones. And so because most of the universe is empty space, the sky can appear dark even though every line of sight eventually intersects a source of some kind. Every line of sight does intersect a source, but most lines of sight intersect the last scattering surface, not any intervening star. And so the last scattering surface appears faint because of the redshift factor. And so the reason that we solve Olber's paradox is there was a start to the universe in a finite age. And in fact, almost all the non-local radiation we receive is from the last scattering surface. This is in fact what we see as the night sky, with some intervening galaxies superimposed, but they make a very small contribution to what we receive. And so the cosmic background radiation, this is actually the current Olber's paradox resolution. That's what we see. The real result is the temperature of the sky is not the same as the surface of the sun. It's 2.75 K, and it's resolved because of the finite age of the universe. Just a side remark on this darkness is necessary for the existence of life because the Earth operates as a heat engine. It receives high-grade thermal energy from the sun, which covers a very small part of the sky. It disposes of low-grade thermal energy to the rest of the sky. This heat engine wouldn't be possible if the entire sky was as bright as the sun. If, in fact, there were stars covering the entire sky so we couldn't see the last scattering surface because there were too many stars in between, life wouldn't be possible because the surface of the Earth would be at the sun's temperature. At the moment, the incoming radiation is balanced by reflected and outgoing radiation because the sky is a sink for waste energy. Now, there's a gravitational version of Olber's paradox. The same issue arises in Newtonian gravitational theory. For that too is an inverse square law. The contributions to the Newtonian gravitational force diverge in principle, which is why Newton never succeeded in creating a cosmological model. The present-day form of this problem arises in studies of the large-scale motions of matter induced by the gravitational field of large-scale inhomogeneities, such as the great attractor. The question is, you go out a certain distance, you've got exactly in your surfaces, if you do a Newtonian calculation, you get the Olber's paradox all over again. How far out can you cut it off and say we've gone as far as we need to go in those calculations? Do we need to consider further out matter in our calculations of those integrals? Well, in the space-like version, the Newtonian force acting on the great attractor and so on, there's some major difference from Olber's. Firstly, the integral is in space-like surfaces rather than on the past light cone. So you can't rely, as I did in Olber's paradox, on the finite age of the universe. It doesn't help. If we lived in an infinite space section, in principle, you do have to take it out to infinity. But there's no natural cutoff in that case. If we have infinite spatial section, one must in principle extend it to spatial infinity, and it diverges. But this is compensated by the third point. Although the gravitational field in principle diverges, its local effect is vector in nature. Because in fact, for each pull going that way from the matter over there, there's an equal and opposite one pretty much from the matter over there. And so the vector nature of the gravity actually helps solve the divergence in this case. Thus, in effect, one renormalizes by omitting the divergent integral due to a uniform background and only calculates the remnant effect due to inhomogeneities superimposed on this background. So the conclusion to this section, we can never prove the universe is infinite in size. If we show k is -1 or not, this does not do the job. It does not show the universe is infinite. If it was infinite, it raises philosophical problems, the infinite duplications and repetitions. And I emphasize this is a philosophical problem. It's not something you can rule out by physics, but it's the kind of thing which you can, if you wish, use as a super selection principle. You can say that there are selection principles for meaningful solutions, and you might, like Einstein and Wheeler, say, I will only accept solutions where the answer is finite. It does raise, in my opinion, physical problems, how a genuinely infinite amount of stuff, not just a very large stuff, could be created. If there's a creation event, if you think about it, there's a huge difference between creating a finite amount of stuff and an infinite amount of stuff. Remember the nature of infinity. It's more than anything you can ever think of. It's more than anything you can count. If you think of a creation process, it seems to me that, at least in principle, there's a major difference between creating a finite amount of stuff in the universe and an infinite stuff. People don't seem to talk about that. In my opinion, the assumption the universe is infinite is dubious philosophical position because it can never be tested science. We don't know what happens outside the horizon, and I'll come back to that point, because it occurs again in the existence of the infinite multiverse. And this is the same as the last one, excepting even more so. The idea of a multiverse, an ensemble of universes or universe domains, has received increasing attention. Separate places, separate times in a cyclic universe, the Everett quantum multi-universe, other branches of the wave function, the cosmic landscape of string theory, embedded in chaotic cosmology, or totally disjoint as Sciama and Tegmark. So there's many different ways people have suggested in multiverse, and they usually use the word infinite, usually. So the variety of multiverse, Brian Greene advocates 9 different types, invisible parts of our universe, and of course there is a horizon. Nobody sensible believes the universe comes to an end at the horizon. Obviously the universe continues beyond. Chaotic inflation, brane worlds, cyclic universes, the landscape of string theory, branches of the quantum mechanics wave function, holographic projections, computer simulations, and all that can exist must exist, the grandest of all multiverses. This is according to Brian Greene, the various types of multiverse we can imagine. Well, they can't all be true because they conflict with each other. So you've got to select between them. And of course, how can you choose between them? This is one of the interesting things. Maybe none of the above, maybe there's just one universe. The key observational point is the domains considered are beyond the particle horizon and therefore unobservable. And so this is the same picture we had before, but this is in real physical distance. Here we are now. The past light cone goes out. It reaches a maximum size, and then gravity pulls it back in as you go back towards the past. These are other galaxies. We see that galaxy emit light there, and we see it up there. And this is the Big Bang. But of course, you can't see the causal stuff that's going on. So we go to co-moving radial distances in conformal time, and this is the picture we've already seen, co-moving coordinates. So now the galaxies are vertical world lines. Now the light cone is a nice 45 degrees. Distances are totally misrepresented, times are misrepresented, but we can see the causal structure very clearly, and we can see that this is the last galaxy you can see. You can't see stuff out there because this light cone intersects the surface of last scattering there, and you can't receive light from there because there hasn't been time for it since the start of the universe. So that's the visual horizon. This is the observable part of the universe, the last scattering surface, and the start of the universe. So this is a better scale. That's the observable universe domain on the left. And when we claim there's a multiverse, we're saying that from what exists here, we're predicting what happens out there. But there's no observational data whatever available. There's no way you can get any signal from there over to there. On a better scale, it looks like that. We're extrapolating to the unobservable domains, and the assumption is that from what happens there, we can tell you what's happening over there to 100 Hubble radii, 10 to the 100 Hubble radii, or infinity. And as I've said, the word infinity is very, very often used in these discussions. This is not testable science, and the situation won't change. Someone said to me, well, what about if we wait for another 14 billion years? It won't make any difference. This is not an observation testable proposal, therefore it's philosophy, not science. And by the way, there's nothing wrong with philosophy. I'm all in favor of philosophy. That's what this meeting is about. But one of the possibilities, for instance, is you might head out that way and you might end up back where you started. perfectly possible. What about extrapolation of what we see? And Martin Rees has advocated the slippery slope. There are plausibly galaxies beyond the horizon where we can't see them. Plausibly many different expanding universe domains keep on going, and you predict there's the multiverse. But it's an untestable extrapolation because it assumes continuity that may not be true. Outside, there might be a Robertson-Walker model. In the old days, when I was a student, we assumed the universe was a Robertson-Walker model. We took that seriously. The cosmological principle that Bondi wrote about, and Weinberg wrote about it in his book. If you've got chaotic inflation, then the cosmological principle isn't true because you come to domain walls where things change. There could be a closed model, we come back. There could be an island universe. Maybe out there we live in a lump of stuff, and way, way out there things are actually asymptotically flat. If I say that's a possibility, there's no way you can prove me wrong. There's no way I can prove that I'm right because it's all totally unobservable. If we take this seriously, it leads to the idea of spatial homogeneity forever the cosmological principle, rather than the multiverse of chaotic cosmology with domain walls separating the phases. But you can't assume that the same conditions will hold forever. I used as an example many years ago an ant in the Sahara Desert. He's at the top of a sand dune. He looks around and he says the entire world is made of sand dunes. Well, he got it wrong. You can extrapolate, but there's no way you can tell if that extrapolation is correct. And please remember again the nature of infinity. You can extrapolate to 100,000 million Hubble radii. You haven't begun on the extrapolation involved if you claim there's an infinite set of stuff out there. Is it implied by known physics that leads to chaotic inflation? The key physics, Coleman-DeLucia tunneling, the string theory landscape, and particularly the connection between the string theory landscape and the tunneling process is extrapolated from known and tested physics to new contexts. The extrapolation is unverified and unverifiable. It may or may not be true. The physics which is claimed to lead to chaotic inflation is not tested in known physics. Does known physics lead to the multiverse? No. Known physics leads to hypothetical physics leads to the multiverse. There's a major extrapolation from what we know to the physics which is assumed to predict for you without any doubt that the multiverse exists. It's a great extrapolation and it's untestable. It may or may not be correct. And this, of course, is because we can't test physics to infinite energies. There's what I call a physics horizon as well. There's a limit to the highest energy we can test. That's another of these limits. We can't test to infinite energies. We can't test the energies relevant at those very early times. And you get the measure problem. I think other people are going to talk about this. We have to give sense to relative probabilities. There's a global time cutoff. There's a global patch measure. There's the measure problem for eternal inflation, various probability measures. I'm not going to go through all of this. I think other people will talk about this. There's a Youngness paradox, a Q catastrophe, freak observations, a lambda probability. All I'm going to say is all of these problems arise because of the assumption of an infinity of model in the universe. Alex Vilenkin goes on to posit our universe is but one of an infinite series, many of them populated by our clones. Vilenkin is well aware of the implications of this assertion. Countless identical civilizations are scattered in the infinite expanse of the cosmos, with humankind reduced to absolute cosmic insignificance. Our descent from the center of the world is complete. This is a use of the paradoxical properties. He emphasizes, he repeats what I said with Brundtland many years ago. It's doubly untestable because of the horizons and because you can't count to infinity. Now, there's one really interesting one, and this is one I do have to answer. The claim is that you get tunneling and a tunneling event, and the really interesting thing is the possible. If a tunneling event there in the De Sitter universe creates a new patch, this hyperbola is at the same constant distance from there. So take it 1 second. That's 1 second. This hyperbola extends to infinity is 1 second away, and so you can say that all of those points are at the same proper time and extends to infinity. So the claim is a very interesting one. I create a thing there, and this 1 second later, this entire space section has been completed, and so I create infinite space sections instantaneously here, because the smaller, no matter how small the time is, those hyperbolae stretch to infinity. So I therefore create infinite space sections. Infinite space sections appear at once. Now, what's wrong with that argument? The answer is it depends on the idea of a point there. And I wrote about this with Bill Sturger. If you allow for the fact that nothing can happen at a point, that there's a finite radius there, no matter how small that distance is away from there to there is a much longer time than from there to there. And from there to there is a much longer time. And in fact, because things can only happen in a finite time, this creation will proceed up. It won't take place at an instant. It will proceed upwards because that time is increasing all the time up there. And so, in fact, the claim that an infinite section is created instantaneously is not a good claim. It depends on the idea of something happening at a point. It can't happen at a point. This is this duality between 0 and infinity. It's not true if you remember the origin can't be exactly a point. In fact, it takes an eternity to complete, and you can create a space section which will be infinite, but you will never reach the infinite space section in a finite time. It's always in the future. You always will reach it some stage in the future. So the real question is, how many domains or galaxies exist at what time in the multiverse? I think this is the real question. Chaotic inflation had a start, we're told by Guth et al. At any finite time after the start, there'll be a finite number of bubbles in existence. The measure problem will be ameliorated in this context because there's only a finite number of existing entities. So the real need is reformulate the multiverse theories in this context. How many bubbles do you need to make an anthropic argument work? Don't talk about infinity. Tell me a number. How many you need? How long after the start will they exist? Give me time. That's real physics. Forget those infinities. We tame infinities by putting in realistic limits. So my conclusion of this first lecture: we can never prove an infinite multiverse exists. We might show a few bubbles exist. Through bubbles collisions, that's not an infinity of bubbles. If it was infinite, it raises philosophical problems, the infinite duplications of events. It raises physical problems, how a genuinely infinite amount of stuff, not just a very large stuff, could be created. The assumption that the multiverse is infinite is a dubious philosophical proposition and can never be tested science. So I finish off by reminding you of my basic statements. The true nature of infinity, it's not a very large number. It's an entity that can never ever be obtained. It is always beyond the bounds of the possible. And so I'm proposing the basic guidelines. Infinities do not exist in real physical systems, and the infinity fork. If the use of infinities in a physics argument is essential, the argument should be discarded, in my opinion. If the use is not essential, replace it by a large number and effective infinity and work out what it tells you by finding out how big is that number. That's telling you real physical things.